This is section 4.4, L'Hopital's rule and indeterminate forms of a limit. So example 1a is something I want to review I did in class. So as evaluate the limit as x goes to 0 of e to the 2x minus 1 over e to the x minus 1. So if we try to plug in x equals 0, we get 0 over 0, which we learned in chapter 2 is the indeterminate form. So now we have this new rule called L'Hopital's rule, which can be used for the form 0 over 0. I've indicated that I was using L'Hopital's rule by putting an L'H underneath the equal sign. You're not required to do this, but I will always do it just to really call out that I'm using L'Hopital's rule. All L'Hopital's rule is taking the derivative of the top part of the function over the derivative of the bottom part of the function. So the derivative of e to the 2x minus 1 is 2e to the 2x, because I'm using chain rule here. And then the derivative of e to the x minus 1 is just e to the x. So in this case, I was able to just plug in now x equals 0 and get a value that was determinate. I got 2, so that's the answer. So one thing I mentioned in class was sometimes when you plug in, you might still get 0 over 0 after applying L'Hopital's rule, or something like infinity over infinity, an indeterminate form. But if you see some algebra that you can do, then you should do that and then try again. So that didn't apply in this case, but just a tip there. So I also mentioned, we were running out of time, but I just mentioned that in this case we could have actually done some algebra to do this one. We didn't have to use L'Hopital's rule. And so I put that in the brackets there just to show that work, that yeah, we could have used algebra on this one. So now I want to continue on with another example. Let's find the limit as x goes to 0 of e to the 2x minus 1 over x, which is kind of similar to our last one. Now if I try to plug in here, I get 0 over 0 again. Note that algebra is not possible for this one in order to determine this limit. So now we don't have algebra as an option to solve. But L'Hopital's rule applies. And so the point here is that this rule, L'Hopital's rule, is allowing us to evaluate a limit for which we didn't know how to do before. I'm going to apply L'Hopital's rule by taking the derivative, or finding the limit I should say, as x goes to 0, of the derivative of the top, which is 2e to the 2x, over the derivative of the bottom, which is 1. And then this just reduces to 2 times e to the 2x. I'm going to plug in 0, so I drop the limit notation and just plug in 2 times e to the 2 times 0, which is 2. Let's do another example. The limit as x goes to infinity of the natural log of x over x. So as always, we try to evaluate this limit from the get-go. As x goes to infinity, the natural log of x also goes to infinity. As x goes to infinity, x goes to infinity. So what we have is the form infinity over infinity. This is one of the forms for which we can use L'Hopital's rule. Before I get any further, I should backtrack and remind you that you can look at the function here of natural log of x to help you determine that limit. Try a little bit more obvious here, that this function does increase and then it does not have a horizontal asymptote. It does go to infinity, although more slowly than like a polynomial or e to the x or something. So, but it does go to infinity as x goes to infinity. So I was using this end behavior to determine the limit as x goes to infinity of natural log of x. Alright, so all that was just, can I determine the limit? No, indeterminate form, but also what I was doing was checking to see if I could use L'Hopital's rule. if it wasn't determinate and of the form 0 over 0, or infinity over infinity, or negative infinity over infinity, or equivalent to those last two cases with the signs. So I'm saying, hey, I'm going to take the derivative of the top and bottom. The derivative of natural log over x is 1 over x. Derivative of x is 1. So now this is easy to do. We learned with that theorem 5 that we used a lot in section, whatever that was, I think it was 2.6, limits at infinity, that the limit as x goes to infinity 1 over x is 0. So we have 0 over 1 here, which is 0. And in this one too, algebra was not an option to solve, which I won't even write down, but the point here is that L'Hopital's rule is allowing us to do a limit for which we couldn't do directly by algebra.